In this video, we're going to be looking at this problem, meeting rooms 2. So we're given an array of meeting time intervals where intervals I is equal to start I, end I, and then we want to return the minimum number of conference rooms required. Let's take a look at the examples to get an idea for this question. So in the first example, we have these intervals 0:30, 5:10, and 15:20, and the answer is 2. It's easy to see why we need a minimum of 2 conference rooms. The first room holds the meeting from 0 to 30, and the second room holds the meeting at 5 to 10, then 15 to 20, and this is because they don't overlap, but they would overlap with the first meeting. In the second example, we have these intervals 7:10 and 2:4, and the answer is 1. We only need one room because these meetings don't overlap, as first there's a meeting from 2 to 4, then there's a meeting from 7 to 10. So this is a pretty intuitive problem because it's something that occurs in real life with employees booking meetings at a company. On one hand, when an employee books a meeting room, you want to be able to actually allocate a room to them which doesn't conflict with another meeting happening in that room at the same time. But on the other hand, you don't want there to be too many unused rooms, as this would imply that meetings are not running in parallel as efficiently as possible. Okay, let's break this question down. Let's say that we're given some list of intervals. So for each tuple, the first value is the start time and the second value is the end time. So the first thing to note is that it doesn't make sense to process these intervals in any random order. Instead, let's sort them by their start time in ascending order. So this is because naturally we want to allocate meetings that start at earlier times in the day before processing the ones later in the day. So then that gives us this. Now let's try allocating these meetings to rooms manually by hand. So first we have 1:10, so we're going to need a room. Then we have 2:07, but in room 1 the meeting is still ongoing, so we need a second room. Then we have 3:19, same thing. Both rooms 1 and 2 have meetings that are still ongoing, so we need a third room. Then we have 8:12, which can be allocated to room 2, since this meeting happens after 2:07. Then we have 10:20, which can be allocated to room 1, as this meeting does not overlap with 1:10. Finally, we have 11:30, but no rooms are available at time 11, so we need a fourth room. And therefore, there must be at minimum 4 rooms for all these meetings to be allocated without overlap. It's pretty straightforward to reason why this algorithm is correct. Because we sorted the intervals by their start time, we know that upon allocating a meeting to a room, we know that that meeting is the earliest that could occur in that room. Therefore, we minimize the unused time in between meetings in those rooms. Essentially, we're packing the meetings as tightly as possible. So sorting the meeting intervals at the time in the beginning is straightforward, but how do we efficiently find out if a room is available or not? So when you look back at this algorithm, for each meeting that we're attempting to allocate, we really only care about which room has the minimum end time. If the meeting start time is less than the minimum end time, then we know that we must allocate a new room. Otherwise, the meeting will be allocated to that room with the minimum end time. So here we can use the min heap data structure. If you recall, this data structure allows us to query for the minimum value efficiently. So let's write this in pseudocode first. So first we're going to sort the intervals by start time. We're going to initialize a min heap. And then we're going to first add the first interval's end time to the min heap. Then we're going to iterate over each interval. So when we actually implement this, we are going to skip the first interval, of course. So we're going to peek the heap's minimum value and then assign it to a variable. Let's call this min end. Now, if the start is greater or equal to min end, well, this means that we are able to assign this interval to that room. So then let's remove it from the heap. And then let's add the end time to the min heap. Then let's return the min heap's size. which will essentially give us the minimum amount of meeting rooms required. So let's test this out so that we can verify that this actually works. So first we have these intervals sorted by start time. So we're going to initialize the min heap. So let's call this PQ because it's usually implemented as a priority queue. So first we put 10 in there. So 10 is the minimum end time. Then for 2, 7, well, 2 is less than 10, so we add 7 to the PQ. Then for 3, 19, well, 3 is less than 7, so we add 19 to the PQ. Then for 8, 12, well, 8 is greater than 7, so therefore it can be allocated to the same room. So then we pull PQ by removing 7, and then we add 12 to the PQ. Then for 10, 20, well, 10 is greater or equal to 10, so we pull PQ by removing 10, and then we add 20 to the PQ. So now 12 is the minimum end time. Then finally for 11, 30, well, 11 is less than 12, so we add 30 to the PQ. So the size of PQ is 4, so we return our answer of 4. Great, so this algorithm works. So what's the time complexity? Well, sorting is going to be n log n. And then at this point, well, we're going to iterate through n intervals, and then polling and adding values to the min heap costs log n. So total, this loop is going to cost n log n as well. So in total, the time complexity is going to be O of n log n. For the space complexity, in the worst case, all the meetings have to be allocated to separate rooms, which means that the min heap will grow to at most include all of the n times. So thus the space complexity is going to be On. Okay, now let's implement this in Java. So we're going to start off with this edge case, which is when the length of intervals is 0 or 1, where we're just going to return the length. Then we're going to sort the intervals by their start time. We're going to use arrays.sort. And then we're going to pass in this lambda function. As you can see, we're comparing the first element of the array, which is the start time. Then we're going to initialize the priority queue. And we don't need to worry about passing in a comparator because by default, it's a min priority queue. And then we're going to add the first interval's end time. Then we're going to iterate over all the remaining intervals, excluding the first one. We're going to have this variable called min end, which is where we're going to peek at the minimum value in the priority queue. And then, as we said, we're going to check if the start time is greater or equal to the min end. And in this case, we're going to pull from the priority queue. And here we're going to add the end time. And then we're just going to return the size of the priority queue. And great, as you can see, this solution works. And that's how you do this problem, meeting rooms 2.